Thank you. So hello everyone, welcome to this tutorial on memory-centric computing. First, I would like to apologize for my voice. I don't know what happened, but I got to to my voice got weird. But hopefully I'm going to have enough voice to go through the tutorial. So I'm Geraldo. I'm a PhD student in the Safari Research Group, devised by Professor Onur Mutlu. I work mostly on the topic of memory-centric computing or processing memory. I've been working on this topic since my master's in 2016. So it has been like 8 years or so. And if you find anything related to this tutorial interesting, and if you like to reach out, feel free to reach out to me via email. I'll be glad to talk. So as I said, I do mostly research related to computer architecture and process memory architectures. But we also, and I'm going to briefly talk about here of other topics like memory security and systems. So this is the agenda for the tutorial. So this first is going to be quite hectic. And if you ever had the opportunity to see one of the talks of my advisor, Professor Mutlu, you might know that I have a lot of slides to cover. And how much am my screen just frozen? I think we lost the monitor. Just a second. Okay, we're back. Oh, it's quite unstable. Okay, hopefully it works. So in the agenda, I'm going to first give a motivation related to memory-centric computing. Then I'm going to talk about real-world implementations of this new type of architecture, and also a different way of thinking about memory. So using memory cells themselves to do computation. Then we're going to have the lunch break. And then I'm going to talk about, after the lunch break, processing memory programmability. And if time's allowed, we are going to go through a hands-on tutorial on programming one of those real processing memory architectures. If we don't get to the very end, I invite you to check our website. Over there, we have the material for all of the lectures, and also the material for the hands-on tutorial is there. So if you want to go offline over the tutorial, you can follow up by yourself. And if you have any questions or any doubts, feel free to reach out to me. So without further ado, I'm going to start with memory-centric computing systems. So the problem that we are trying to deal over here is that computing is mostly bottlenecked by data. And data is really key for many applications. So for example, I have many important workloads that operate fundamentally over a lot of data, like genomics or generative AI. And the amount of data that these applications are consuming is also increasing. AI is a great example nowadays. If you go to the computer architecture conferences, you're going to see a lot of those architectures being used to accelerate transformers, for example. But it's not only AI, it's the same problem in genomics or in classic problem in databases, for example. And this is just an example from a talk from, I think, from the, I don't remember if it was Grok or Cerebras, one of the two. And they are talking about the growth of data for neural networks over the past few years. So here in the x-axis we have, we can see that from the first bird models to GPT-3, we have an increase of 4 orders of magnitudes of the amount of data that those models were consumed in only 2 years. And the projection is for this to increase further and further down. And as I said, this is not only in machine learning accelerations. This is a classic problem in databases, in data center, in graph processing. And in all those cases, data leads to a performance and energy bottleneck in those systems. So, and it's not only, if you think about this problem in data movement, you might think about cloud computing or computing over a large amount of servers. But we did studies for consumer devices. So looking at your phone, for example, and we see the same pattern being repeated. So we went to Google and we did some analysis of the Google Edge devices, and we figure out that even in your phone, computation was being the main bottleneck for both performance and energy. And as I said, this is just an example of how data is growing in other workloads like genomics. You can see that in the past few years, the amount of genomic data that we have been sequencing is increasing over and over. And in those really specialized sequence machines, we encounter the same problem. So why this is the case? This is the case because the way that we think about designing computers, right? So we have been designing computers following the von Neumann approach for 4 decades now, probably more. And in this von Neumann model, we designed the system where each component of the system has its own responsibility. So have a component of the system for computation, another one for storing data, and another one to moving data around. And even though this has been working for many years, now what we have is that this logic separation between those components is creating a big problem. So just to illustrate how this von Neumann architecture creates a problem, so this is an old picture of an Intel processor, and you can see here the green part is what the red part is the part of the die that's responsible for computation, and everything else is responsible for or either storing data or moving data around. So the majority of the chip there is actually just there to either store or move computation. And yet the system is bottlenecked by main memory. So if you look at newer processor chips, we see similar problems. So this is a AMD processor, and in the green part over here, and I don't have a pointer. It does not get there. It's really annoying. But in the red part, the green part over there is where your caches are sitting. So the core count, the cores themselves are not occupying so much space. And this is, if you look at 3D architectures, it's pretty much the same, or other processors from other vendors like IBM or Apple. This is a picture of the M1 chip here, and in this picture is really interesting because you can see clearly a lot of SRAM memories, a lot of DRAM, and there is a black in the corners. That is actually the majority of the picture, and this actually is storage. So this is to say that if you look at the die of this really advanced processor, the majority of the die is actually just for memory. And as for the motivational data, as I mentioned, we did this study together with Google, and we saw that for the Google phones, around 62% of the total system energy was being spent on data movement. And if you look at edge accelerators themselves, like we did the same, we repeated the same study with the Google Edge CPU accelerator, and then we saw that more than 90% of this total system energy is for those really specialized ML accelerators were being spent on data movement for some data-intensive models. So the problem, again, to make it more clear, is that data excess is creating a performance and energy bottleneck in current systems because of the way that we are designing such as systems. And this is not, this is leaving a lot of performance and optimizations on the table. And the main, and if you further down think about the problem, you can think that the problem is that data is being processed really far away from the memory. So if you have your centralized processor sitting in some portions of your system, of your chip, and your data is on the storage or in a disaggregated memory, you need to bring the data to that process, to inside that processor for doing some computation. And this communication is the main source of data movement bottlenecks. And this is not a new thing. Research sites published this paper in 1996 called "Is the Memory Stupid?" So in that paper itself, he already foreseen that in the future, memory will be the most important problem to optimize for in processors because of the trend where the processor frequency was increasing because of Moore's law, but the memory bandwidth and the memory latency was not increasing at the same pace. So, but now this is becoming a realization of this problem. So this is a example of Onur's PhD thesis, and where he went to Intel and he did some analysis of some Intel workloads, and he saw that the majority of the more than 50% of the execution cycles were expanded on installs because of off-chip memory requests. So this is from 2003, so there was no L3, so that's why off-chip was based on L2. When we are not the only one looking at this, so Google also published this paper in 2015 called Profiling Warehouse Computing, and where they profile their main applications. They were running on Google data centers, and they came to the same conclusion. They saw that for some of their key workloads, the majority of the time, so this purplish part or reddish part here was being spent on moving data, and the green part is the parts that the computation is being done. So we are retiring instructions. So you can see that's the smallest part for those operations. So what is the problems of this? What we call this processor-centric systems, because the processor, everything happens based on the processor request. So we have a grossly imbalanced system because computation is only performed in a single place, and for every single computation you need to move data back and forth the place that the data is stored to the processor itself, and this causes energy efficiency, low performance, and complexity. And then what we are doing to tolerate this data movement is to create more and more putting more and more complexity into the system. So now we have levels and levels of cache hierarchy, levels and levels of aggressive hardware prefetchers, and all of those are there just to try to circumvent this problem, and still you're observing the same problems. So from an energy point of view, the problem that we have is that every time that you go off your energy, your overall system energy is bottleneck, is dominated by that off-chip communication. That's because you're going from inside the chip through the pins to the PCB of the other chip. So just an example, if you have to doing a memory access to DRAM to doing a double precision float point operation in the chip, that request to DRAM takes around 100 times more energy than doing that simple computation. And this is another way of looking at the same data. So here we have different operations, and in the y-axis we have the energy normalized to a 32-bit arithmetic operations, and then we can see, of course, all of this depends on the system that we are looking at, and around this behavior is observed in those different systems. So the number itself might change, but the fact is that doing off-chip communication to your main memory or to your storage takes 2 to 3 more energy than doing a computation inside the memory device itself. So to solve all of these problems, we need to think differently. We need to have a paradigm shift, which can enable us to do computation with minimal data movement and compute where it makes sense. So our goal is to move the data the least amount of times to achieve some computation. And for that, we need to have a more data-centric computing, data-centric view of current systems. So the axiom that we use to design such a systems is that if you want to have an intelligent architecture, this intelligent architecture needs to handle data very well, because as I mentioned in the motivation, data is the main cause of performance and energy loss. And we can do this in different ways. So we can do this by designing better algorithms. People have been doing this for example, for tiling for caches for many years. But we need to think further on the stack. We can think about doing intelligent architectures and also having a more holistic view of the entire system. And all of this can allow us to look at of this vast amount of data not as a problem, but also as an opportunity to understand better and design better systems that are more driven based on the data. So as a corollary, we are going to have this battle between the current processor-centric systems versus these data-centric systems. This designer dictated decisions versus more data-driven decisions. A small view of the system versus a more data-aware view of the system. And in the very end, what we're going to get is an intelligent machine that can be data-centric, data-driven, and data-aware. And to do that, we are going to have to revisit the entire computer architecture stack from the algorithm point of view down to the gates and the implementation of the architecture itself. So, so this is just an introduction of this new concept of data-centric architectures. Hopefully it's more or less clear. And now I'm going to start talking about what are the properties that we want in these systems. So for us to have a more balanced system, we need to first process as I mentioned before, process the data where it resides. So we want to move data as fewer amount of times as possible. We also want to have data access that are more low energy and performance efficient. So you want to have low latency and low energy for data accesses. And the same goes for storage. So you want to have more efficient storage systems and more intelligent ways of handling data across this entire system. So if I show you this picture again of the Apple M1 processor, and you have several different components of the system, the question is, where does it make sense to compute? Because right now the computation is dictated based on the volume architecture that is in the center of is in a single place in the system, right? But why should I choose? Why do I need to choose if I want to compute in a single place? If my data is stored in the red part in the storage, maybe I can just do the computation over there. Or if my data is stored inside the green part, the DRAM, maybe I can do my computation over there. But to do that, we need to think differently. And we are going to have this mindset now, where we are going to think about memory not only as a passive component of your system, which stores data, but we are going to think about memory as a specialized accelerator. We are going to, so basically what I want is to tell my memory, and here is the RAM or your storage or your cache, don't just give me a piece of data. I'm going to give you a query. I'm going to give you some filtering or some scan. Do this operation for me and return the output. And this, with this simple specialized view of memory, we can save a lot of these performance bottlenecks and energy bottlenecks. That would be caused if you want to move the data back and forth the memory and the processor. So this is really conventional to a similar accelerator, but we are going to start building and building on top of that as we go. So this idea of treating memory as an accelerator is not new. So the first paper that we are aware of that comes up with this concept is from 1969, cellular logic in memory, and then there is another paper from around the same year, logic in memory computing, and where they advocate for adding some computing near my memory arrays themselves. And we have been seeing waves that this idea comes and goes. So in the 70s, as I mentioned, this initial idea was proposed, and then it died out, and then later on in the late 90s, Peterson and his group in Berkeley, they came with this intelligent RAM architecture where they were designing some memory chips with some processors inside the nearby the chip itself. But at the time, it was not commercially interesting, or there was no much push for this type of system, and then it died again. But now, as I'm going to show in the later slides, we are having a new wave of this type of architectures because we are having a push from the application domain itself. So the majority of the memory manufacturers, Samsung, SK Hynix, they all have been releasing architectures that follow this memory-centric approach. So what are the so why we should do in-memory computing today? So why this new wave is being generated? And it's because of at least three main reasons. So the first one, we are having a huge problem in terms of scaling memory cells themselves. So memory cells got so small, and the memory chips are so dense that now we are having some reliability phenomena happening in the memory cells themselves, creating some security problems that I'm going to mention next. The second problem is that we have a demand from applications and systems. So I mentioned before machine learning, right, or genomics, and those applications are quite dominating. They dominate the current landscape, and they require fundamentally for them to operate well, they're required to read and write a lot of data, and this is just exacerbate this imbalance that von Neumann architectures actually have generated, like performance and energy problems. And the third problem is that now the memory itself, the memory model, is sitting in the middle of these two these two problems. The problem from my memory is not scaling good enough, so I can provide good performance, and my application is requesting more and more memory, which I cannot provide. And at the same time, we have been seeing some technological advancements on memory manufacturing themselves. Perhaps the more important one from the last 5 years has been 3D stack memories. So in 2012, I guess some memory manufacturers came with this memory consortium from these 3D stack memories called the Hybrid Memory Cube. It died out, but there was other solutions that now are quite common in GPUs, for example, like hybrid bandwidth memories, like HBM memories. And those are memories that we stack together memory chips and connect them with some silicon vias. But it's not only about 3D stack systems. Even in 2D stack systems, memory manufacturers are taking the risk to implement some computation. Like we have this, I'm going to talk about the upmapping system, for example, or the Samsung HBM chip that actually is not called HBMP anymore. I think it's called Aquabolt or something like that. Samsung keeps rebranding this device, or SK Hynix, and there's another chip from Samsung and Alibaba. So the landscape is much broader nowadays for these memory-centric chips because of this push from both technology, and applications. And if you are curious about this scaling problem that I mentioned earlier, I invite you to check this paper, the Memory Scaling System Architecture Perspective. But I'm going to give a briefly detour to talk about this memory scaling problem that is being caused by the density of memory devices themselves. So there is this phenomena published in ISCA 2024 that one can predictably induce errors in most modern DRAM chips just by accessing data. So this is called the Rohammer phenomena. So what we have inside the memory chip itself is this 2D array of memory selves, and where data, when you want to access data, you open one of these rows by applying some high voltage to the word line, and after you are done with this reading this data, you close this row by putting the voltage low. So if you keep doing this, opening, closing this row, eventually we can inflict bit flips in nearby DRAM rows, and these bit flips have been shown to be useful to take over systems or to leak secure information. So and this is basically caused because the memory cells themselves got so small over memory scaling over the years that the charge can float across the different rows and causing these bit flips. It's quite, and this is the initial study that we did from 3 main memory manufacturers, and we saw that all of those actually, we can induce all of those bit flips in all of those memory devices themselves. And this is quite old, 2014. Later on, we did a second study for newer DRAM chips, and then we saw that this behavior is actually getting worse over the time, and it's just now in the latest JDEC. JDEC is the consortium that stipulates the properties of the manufacturing of memory chips. So just now, in 2024, the current specification defines a way from where you can potentially prevent this type of row hammer induced bit flips. So we are not the only ones reading or like worrying about this. Google, I forgot the name of the project, but around the same time, Google observed a similar problem, and this is the paper that I was mentioned later on. And if you are interested in this row hammer problem, I invite you to check our retrospective paper, and we keep working on trying to understand this problem better and better over the times, and we have a bunch of publications and videos online about them. So this is a push. This is just to illustrate this problem that we are in the very limit of the memory scaling from memory devices. So we can look at this problem from another view. So maybe, okay, we cannot scale the memory, but we can maybe design better memory controllers to mitigate this problem. And now industry is looking into those more specialized memory controllers that can somehow improve, for example, security. So this is a paper from SK Hynix in ISCC 2023, where they implement some row hammer mitigation technique inside the memory controller themselves. And there are other examples that we keep seeing. As I mentioned, JDEC just added some of the mitigations in the specification itself. So related as well with this row hammer problem, or this, we call this read disturbance. We can think, okay, maybe it's not reasonable to expect someone to keep accessing a same DRAM row for thousands of time and then just observe a bit flip. But we have seen in our ISCA paper last year that you don't even need to access the rows several times. If you just keep a one DRAM row open for enough time, you can also induce bit flips in nearby DRAM rows and generating security issues for the system. So this is what we call row press. So it's a similar idea of row hammer, but in this case, we are only accessing the row once and keep it open for a long time. So it just illustrates that if you don't start looking seriously to this security problem from main memory, we are going to continue having more and more problems over the years. So, and this is just to say that in the industry, this is a collective paper between Samsung and Intel, where they talk about this is DRAM scaling problem. So, and just the overall takeaway of the tour that I did is that memory scaling is one huge problem for memory manufacturers right now, but we can mitigate this problem by designing better memory controllers. So coming back to the memory bottleneck problem, not necessarily the memory scaling problem, there are three main key systems and application trends that we expect from these memory-centric computing problems. So the first one, we want to mitigate data access bottlenecks as much as possible. The second one, we want to mitigate we're going to look at energy as a key metric, and you want to also think about the amount of data that you are moving inside the chip as much as possible, inside and outside. And overall, you want to design a system that can achieve high performance, high energy efficiency, and sustainability all of the same time. And for doing that, we are going to again think about this scheme where we are going to think of memory as accelerator. So how do we get there? How do we design this type of system? So we need to think about many things. The first one is where we put the computation itself, and what type of communication we need, what type of software and hardware interface we need to support. And also from an application point of view, we need to think about compilers, system support, and all of those. As I said, we need to revisit the entire stack, but we are going to do this one step of a time. So this talk or this tutorial is heavily inspired by this book chapter that we wrote and we keep updating over the years called I'm What the Prime of Processing Memory. So I invite you to check it out if you have any questions. And I think this is the end of, it's not the end yet, but before I end it, I'm just going to give some taxonomy that we're going to use for the next slide. So we call these architectures that can do some computation, processing in memory architectures. Right now, the literature is quite convoluted in terms of the nomenclature, but this is the more general term. You also might find in the literature in-memory computing or near-data computing, the data processing, everything you have been used. But here we are going to use processing memory or PIN as the general term, and we are going to divide these PIN architectures in two categories. The first one is this processing near memory architectures, which are quite similar to the traditional von Neumann architectures in the sense that you still going to have one place where you're going to do the computation, another place where you're going to do store data, but we are going to move the place that we do computation closer and closer and closer to the memory device itself. The second approach is a bit more radical, processing using memory. In the second approach, we are going to forget logic. So you're not going to add gates or you're not going to add LUs to do computation. We are just going to think on how we can operate the memory device themselves in a different way so that we can achieve some sort of computation. And this is completely different from the von Neumann approach, because now we don't have separation between what's memory and what's computation. Both computation and memory are the same thing. So this is the taxonomy that we use in this paper that I mentioned, processing using memory and processing near memory. And in the next slides, I'm going to talk about the processing near memory approach itself. So I talked a lot. I don't know if there is any question before I move to the processing near memory architectures. Okay, so let me do some context switching. Okay. Hopefully Zoom can still see it. Girai, can you still see my screen? Okay, I'm just yes. Okay, so I'm going to start to. Sure. Yes, yes. On the cache and across the entire memory hierarchy. So on caches, on DRAM, or on storage. Also, in the processing memory, I'm going to briefly talk about these systems for flash memories, for example. So, as I mentioned, okay. So now we're going to talk a little bit about processing near memory systems, and I'm going to briefly also introduce the real world processing memory architectures. So where should we employ this new architecture? So in terms of applications, there are proposals looking at employing this type of systems for example, graph processing, machine learning workloads, neural networks, DNA sequence, databases, time series analysis, and many other applications. I'm going to start by giving an example on how we can accelerate graph processing, so portrait chasing, using this type of processing near memory architectures. So graphs, as you probably know, are quite large data structures and quite useful in many applications like Wikipedia or Instagram. And when you look at the amount of computation that we actually do per memory access when you are traversing a graph, usually it's quite small. So this is an example for the PageRank algorithm used in Google. And you can see that basically when you're just doing a multiplication and addition when you are traversing the graph. So you don't do any heavy computation for this. But at the same time, we move a lot of data when you're processing some graph applications. So at the same time, the time that we designed the system, there was, as I mentioned, 2012, there was this memory consortium of this new 3D stack chips called High-Remaining Cube, where the chip itself has two different types of layers. Have these memory layers, which are stacked together. Those are just regular DRAM chips that are stacked using two silicon vias. And there is a bottom layer called this logic layer. And this logic layer is CMOS compatible. So you can design a processor, for example, in its own manufacturer process, and later on glue this processor design together with this memory design using these three silicon vias. So we are going to use this type of architectures to put some simple computation cores inside the memory package itself, so that we can accelerate these graph processing applications. So the
Excuse
type
me,
of
Geraldo.
yes.
Can I interrupt you for a second? There's a question on YouTube.
That would be great. Sure.
Will in-memory computing increase heat in memory device, making them more corruptible?
Okay, that's a good question. So it highly depends. So just repeating the question, someone is asking about the thermal dissipation problems that now we might face when you're doing computation inside the memory itself, and if that might make my memory more corruptible or not. So when you're doing what I'm just mentioning here, these 3D stack type of systems, the basic die, the logic die itself has some quite restrict power and area constraints. So because we are not going to put, this is going to use passive thermal dissipation to dissipate and dissipate heat. We're not going to put a heat sink on top of it, or power budget is quite limited, so that we don't incur these reliability issues when you're doing computation in this chip itself. Even if you look at it to the chip, we also have the same problems. We don't have a source of active heat dissipation. So you're also going to limit the core and the frequency of the core to be quite low. So this is just one design constraint that we need to take into account when you're designing this type of systems. Of course, you can be more aggressive and then decided to put more active heat dissipation in the memory chip itself, but usually it becomes too complicated too quickly. So I guess hopefully I answered the question more or less. So for now, no, because you're designing something really simple, but we are taking that into consideration in the design itself, so that we don't burn the chip, basically. Okay, thanks for the question, Girai. So
yeah,
yes.
Thank you very much, Geraldo.
So just continue about this architecture that is designed for graph processing. This is just a good example of type of simple computation that you're going to enable. So here you're only going to put some in other cores inside the logic die to do this graph traversal itself. And there are some auxiliary things so that we can fully exploit the bandwidth of the memory device as well. So we evaluate this system, and it's called Tesseract, and we designed this Tesseract chip with several memory devices, and it's the overall system can achieve like 8 terabytes per second of throughput. And when compared to other processor-centric systems, we see a significant increase in performance and also in energy reduction when doing graph traversal. And this is the paper published in ISCA. And as I mentioned before, this is not only for DRAM. You can also think about similar architectures for other memory technologies. And I'm going to give an example here of GenStore, which is a processor near a storage device. So targeting genome sequence analysis. So when you have genome sequences, you store your genome, your reference genome on your storage subsystem. And when you want to do some sequence to decide, figure out a new disease variation or some drug processing or something, you need to move the entire genomic data, which is in sometimes in the petabytes of order of magnitude, to the DRAM, to the CPU to do some computation. And this creates computation overhead and data movement overhead. So there is a lot of systems that tries to accelerate this process inside the chip itself using heuristics, accelerators, and filters. And this can mitigate the computational overhead, but still you need to move the data from the storage to these accelerators, still leading to data movement overheads. To solve this problem, we devised this system called GenStore, which basically we have your flash devices, and your flash devices has a simple processor embedded over there to do some matrix operations. So we are going to argue that processor with some filtering capabilities, so that we can filter some of the portions of your genome data, and then hopefully send fewer smaller amounts of data from the storage to the computing unit itself. And this can increase, this eliminates the data movement problem and can significantly improve performance and improve energy efficiency of the system. So this is the GenStore work. And so I gave examples of two systems, right? And and those are more large scale systems. But we can also think about designing such as systems for consumer devices. So we went to Google in 2019, before 2017 or 18, something like that. And we did some analysis of the Google consumer workloads that was running on Google Chromebook devices, for example. And we saw that energy was a main problem. I already gave this data, which in this type of systems, data movement, oh, my computer is lagging a little bit. Data movement was generating, was accounting for 62% of the total system energy for those systems. So our goal was to minimize the data movement overhead for these consumer workloads. And by doing some further profiling, we saw that the majority of the functions that these applications were running are actually quite simple. So, for example, some compression or decompression for video or some video encoding or decoding, which are quite simple operations. So this enables us to design some really simple and small embedded cores that we can, or some fixed function unit accelerators, which we can embed together with the memory itself to do some acceleration. And by doing so, we can accelerate these applications and improve energy by two times. So these are the workloads. I'm not going to go into details on each one of them, but for example, we accelerate this TensorFlow mobile applications by applying this same approach in the packing and unpacking quantization steps of the TensorFlow, and and we saw that again some significant saving in energy and performance. So there are more on this Google Workload paper, and we keep repeating these experiments, or we keep looking at different applications and different type of systems and trying to figure out when we can apply this memory-centric computing approach over there. So we look at, for example, GPUs or other accelerators for different applications to try to improve its performance one by one using these 3D stack systems, for example. I'm not going to get to the details of those. But the next one, if I'm not mistaken, is the yeah, there's several examples of those architectures. And this is the one that I want to illustrate, which is the latest one that we did for, again, for Google Workloads. This is the one that we did for edge devices. So we went again to Google in 2019, and we are looking now at this Google Edge TPU accelerator that is used to accelerate several different models. So we look at 24 different models, like RNNs, LSTMs, CNNs, and we saw that when you are running these models in the Google Edge TPU accelerator, which is supposedly an efficient accelerator for those models, we saw that we saw some inefficiency related to reuse and amount of parameter footprint inside those models itself. So since those models are quite different in structure, so RNN is quite different than a CNN or a LSTM. Designing a one-size-fits-all accelerator is quite inefficient because it leads to, what is my pointer working? Okay. Eventually it's going to come up. So when you are just trying to design a single accelerator, a monolithic accelerator that is fitting several models at once, you end up with a system or accelerator that is quite inefficient in terms of resource utilization. And our idea was, instead of designing a really big accelerator, we are going to design several smaller accelerators with a smaller area footprint and design some runtime system where we can map dynamically the different layers to those smaller sets of accelerators. And this is possible because when you look at neural network layers, they usually tend to groups into families of layers. So usually we have layers that are more compute intensive. Those layers have a small parameter footprint and and large data reuse. And some of the layers are more data centric. Those are the ones with like smaller intensity on the multiply accumulation, the number that they do, and smaller data reuse as well. So this indicates to us that the compute intensive layers would benefit for a more processor centric design, where the data centric layers would benefit more for a processing memory architecture. So we designed this heterogeneous system called Mesa G, which has an area footprint smaller than the baseline Google Edge TPU. And by doing so, we can improve energy consumption by 3 times and reduces and improve throughput for the inference of these models as well with this system. So this is the main accelerator. There are several other examples that I'm not going to from academia that I'm not going to bother you with. But next we are going to talk about these systems in real world. So we in academia have been designing this processing in-memory architectures for quite some time, as I mentioned earlier. But just recently, in 2019, we saw the first commercial available processing in-memory architecture hit the market. And this architecture is called UpMem, and it's coming from a French startup and was released in 2019. This accelerator basically is not 3D, it's not using that hybrid bandwidth memory device that I mentioned before. It's regular 2D DIMM devices. And so when you look at the DIMM, they look just as if any other memory DIMM that you might buy. But this inside each memory chip, we have a simple RISC-V multi-threaded RISC-V processor capable of doing some computation. So this is just some pictures of the current iteration of these chips that UpMem sells. I have 2 versions, one DIMM with 8 chips and another one with 16 chips. And as you can see, they run at quite slow frequency. So the one is at most 350 megahertz. And this is for 2 reasons. The first reason is the thermal problem that I mentioned before, that if you want to clock these processors inside these memory DIMMs at higher frequency, you need some form of a heat dissipation, which is hard to achieve for memory devices. And the second problem is, since this is a 2D chip, the logic and the memory is manufactured together. But the memory manufacture process is optimized for density, while the logic manufacturing process is optimized for speed. So when you mix, when you try to design logic together in the memory manufacturing, you end up with a slower transistor. And this is another reason why you clock those systems at such a low frequency. But this is not much of a problem if you have a throughput system, because the good thing about the compute power of this type of system is that it's scale. The compute power is scales with the amount of memory capacity that we put on the system. So if you have a system, so this is the system that they have in their server. So you have the CPU, some regular DRAM memory from like regular DRAM DIMMs, and this processing memory. And if you increase the capacity of the system by putting more and more DIMMs, you are also linearly scaling the computation power of your system. So this is one of the main advantages of this type of architecture. So I'm going to talk more about this UpMem system later on, but we have some lectures and papers online if you are interested on it. So initially we got access to this we got access to this system, so from UpMem, and we did some initially profiling and benchmark switching for this particular architecture, which is available on our GitHub. And we keep trying to accelerate different applications to see what are the limits of the system, what can you do. So we already accelerate some applications like machine learning, classic machine learning workloads, and we employ some optimizations on top of them. I'm going to talk more about them in details later on. And also other applications like sparse matrix multiplication, and also genomic sequence analysis. Not going to get into the details over here. So this is just the first example of a real process memory system, the UpMem. But later on, 2 years later, Samsung released its own version of a process memory architecture, and was initially called film DRAM. So this is the initial paper that they published in ISC in 2021, and different from the HBM, different from the UpMem chip. This architecture here is going to use 3D stacking to do computation. So they took a HBM chip, and which have several layers of memory, and they remove some of those layers of memory and they put some layers with logic. And this architecture is specialized, is designed specifically to accelerate neural network inference. So the logic that they put in the chip itself is basically some multiply and accumulate SIMD engines to do convolution. So this is their design of their engine, and as you can see, some configurable vector processing type of architecture. And their instruction set is quite limited, but it's limited again because they are targeting a particular application domain. So this is their implementation of the chip, and they keep releasing. Samsung keeps releasing more and more architectures based on this initially film DRAM proposal. So in the previous Hot Chips conference in last year, the Samsung displayed 3 new versions of this processing near memory architecture targeting generative AI. So the main one is targeted to accelerate the GMV in the generative step of transformers, which is dominated by data movement. So this is just a breakdown of the latency. You can see that the majority of the time is spent in GMV, and they do some further profiling, and they see that this GMV is mostly bottleneck my memory device themselves. So to accelerate that, they are using the same film DRAM architecture, now rebranded as HBM PIM, and they integrated in some AMD GPUs, and then they see significant performance gains compared to a single GPU implementation. So this is just one of their prototypes. They have another prototype targeting mobile device, so edge accelerators using low power DDR chips. The architecture itself is the same. Is the same. They also use some SIMD vector processing engine targeting multiply and accumulate, but they are going to use different memory devices as the base memory in case low power DDR memory. And they again see significant performance and energy reduction for some GPT inference. Another example that they are targeting is CXL-based processing memory architecture. So CXL is a memory expander device where you can build disaggregated memory system. So this is just a picture of the baseline CXL memory expander chip, and what they are basically doing is equipping the memory controller of this memory expander with some processing in your memory computation logic, similar again to this NEC unit for the film DRAM architecture. And by doing that, since transformers scales is also a capacity bound problem, they can scale the amount of memory in the system quite easily and significantly outperform systems with multiple GPUs. So this is just the line of family for this HBM PIM architecture Samsung. Early on, they also look at recommendation systems in 2021, and they provide this system that is called IXDIM. This is a bit different type of system because it's more reconfigurable. The original design is using this what's called a LAR DIM. So this is a regular memory DIM, and you have a memory buffer here, and in this memory buffer, they put some reconfigurable logic that we can implement different computations with. And in this case, implement some computations for these recommendation systems themselves. Other systems from other memory manufacturers also comes from SK Hynix. So SK Hynix is pushing a lot, similar to Samsung last year in hot chips. They also implemented some of those architectures. They are here using GDDR6 memory devices. And again, they are targeting transformer inference. So their chip is mostly targeting, the architecture itself is mostly composed of multiply and accumulate logic inside the memory device. This is just a picture of their implementation. Fundamentally, it's quite similar to the Samsung one, but they are just using another memory device. So data center manufacturers like Alibaba are also looking at accelerating their own applications. Again, this is for recommendation systems. And here they are using a different type of manufacturing process. So in Samsung case, they are using 3D stacking systems. The SK Hynix one uses 2D integration. And here they use what's called hybrid bounding, where basically you manufacture a logic and then you manufacture the computation die separately, and later on you glue them together using copper to copper interconnect. So it's just another way of doing that integration. So yeah, with my goal of this was just to give a briefly overview of what is out there in the market for these processing near memory architectures. There are many more to come. We know for a fact that there are other big players like Meta, for example, that are looking to those type of devices. So we're expecting to see more and more of these processing near memory architectures in the future. So I don't know if is there any question related to all of this. Okay, so I don't know how we are in time. What time is the lunch? Is it 12:30 or 12? 12:30, okay. So I'm on time.
Geraldo, can you hear me?
Yes.
So there was a question actually on YouTube,
Can you
and it
hear me?
got removed. And I'm here myself. The question was saying something like, how can we expose this framework to higher levels so that we can use it in the application level?
Yeah, that's a great question. I'm going to try to answer why I'm multitasking. There are different ways of doing that. So I'm going to talk later on the tutorial about the UpMem approach. So what UpMem does is UpMem is a general purpose architecture. So it follows a CUDA-like programming model, so C-based, where the user writes its codes in plain C, and then there is a special compiler that compiles the codes down to this processing in-memory architecture. But this is not the only approach. So Samsung, for example, and also SK Hynix, since they are not general purpose, they are targeting a given architecture, a different application, which is transformers. what they do is that they implement some they manually implement some GMV kernels using those simple instruction set architectures of their target system itself, and they put those kernels together with machine learning frameworks like TensorFlow, for example. And when you are trying to execute inference and your code calls a GenV or a convolution code from that framework, the system, instead of executing the regular GPU code or the CPU code, executes the codes that Samsung or SK Hynix manually wrote for those processing memory architectures. So this is two different approaches. One is more, one depends a lot on the programmer, the UPM one. The other one is completely transparent from the programmer, but it's tied to a single application, which is limiting. But right now in the literature, we have been seeing a lot of people implementing specialized compilers to generalize this type of computation. So I'm going to talk about one of those compilers next in this presentation. But there are a lot of examples. For example, we're using MLR, for example, where you implement a dialect, which is a dialect for these processing memory architectures. And then you can, again, offload computation independently from the user. So hopefully it answers more or less the question.
So the question came back actually, and it says, as a software developer, do I have to rewrite or modify my current code or algorithms, or it will be more seamless? And I guess you already gave the answer. Because as far as I understand, it depends on what kind of PIM accelerator you use, right?
Exactly. So the PIM architecture is more dependent on the programmer, so you need to rewrite your code. The other ones are more independent, but they are fixed function accelerators, so you cannot do much anyway. I believe that there is ideally you should give some responsibility to the programmer because you often need a lot of metadata information to know where what type of data you are manipulating. So, and usually sometimes it's hard to infer that in software on the compiler time, but there is no clear rule set in stone right now for what is the best. So people are actually exploring all of the possibilities and see what is the proper programming model for this type of systems. Okay, thanks so much, Geraldo. So now I'm going to talk about processing using memory architectures. So before I was talking about processing near memory, right? So the computation itself is still quite similar to how you would imagine doing computation. So I have a processor, I do the synthesis of the processor, I place a route inside the logic die, and then I do my computation just inside the memory packet itself. Now we are going to talk about processing using memory architecture. So we are going to forget that process. We are not going to generate a processor or not going to synthesize anything to do computation. We are just going to manipulate the memory cells in different ways so that we can do some simple computation. So let's start very simple. Let's say that I have a memory device, DRAM, and I want to do some data copying and initialization without the intervention of my processor. So this is a common application that is executed by many operating system routines. And Google did a study 2015 showing that 5% of the total, this is aggregated cycles for all of the servers in their data centers is spent on doing this type of operation. So it's quite significant. So if you want to do that in your current system, so I want to copy one address to another address of DRAM, right? So how you do it? So you read the source data you move the source data to the memory channel down to the caches. The processor then reads the destinational data, do the swapping, and writes the piece of data back to the memory. So you need to do this several cache lines at a time. So this process incurs high latency, high bandwidth utilization, cache pollution, and unwanted data movement. And in terms of latency and energy, if you just want to move 4 kilobytes of data from one source row to another one using a DMA engine, so without much intervention of the processor, this takes around 1046 nanoseconds and 3.6 microjoules. So what I actually want, I want to just tell my data, move source data to the destinational data without having this process of going to the processor at all. If I can do that, I can save latency, I can reduce bandwidth utilization, I don't populate the caches, and I don't waste bandwidth on data movement. In comparison, if I can just do that, I can reduce my latency to 90 nanoseconds and improve energy to 0.04 microjoules. So how can I do that? So how can I magically tell my memory device to do that? Before that, I need to bother you a little bit with how DRAM works. It's going to be really briefly. So a DRAM model is organized as several DRAM chips. Inside the DRAM chip, we have several DRAM banks, and inside DRAM banks, we have 2D arrays of DRAM cells, where horizontal DRAM cells are connected to a word line, and vertical DRAM cells in a column are connected to a bit line. So a bit line shares a CS amplifier, and a row of CS amplifier is called a row buffer. And a DRAM cell itself stores data in a storage capacitor, and the data flows from the storage capacitor to the CS amplifier via access transistors. Just another view of the organization of a DRAM chip. We have this share interconnect inside that connects different DRAM banks, and again, it's just another view of the DRAM cells and the row buffer. So when you are accessing data, your memory controller issues 3 main operations to the DRAM chip itself: activate, read and write, or rapid charge. So initially, when you send activate command, the word line for the target row is raised, which connects the storage capacitor to the bit line. And since this is a capacitor, it's going to lose its charge to the bit line voltage, generating some perturbation. The CS amplifier is enabled, and this perturbation is amplified to a CMOS readable value, either VDD or a ground. And then since the capacitor as a transistor is still connected, the charge of the capacitor is restored to its full capacity. So after that, the data is latched to inside the row buffer, and the memory controller can issue several read and write requests from this latched data. If you want to read data from another row, you need to pre-charge the DRAM row by disconnecting the storage capacitor to the bit line, pre-charging the bit line to its reference stage, which is half VDD, and disable the CS amplifier. So this is how it works. So we are going to use that operating principles that I just mentioned to do exactly this operation here of moving one row to another. So the way that we are going to do is with what's called is row clone operation. It's quite simple actually. So let's say that we have a DRAM row and I want to read some data. So I activate row A, and this data is moved to my row buffer. This is just exactly what I mentioned before on how the DRAM already is operating. But now I'm not going to pre-charge that DRAM subarray. I'm going to just issue another activate to my destination row, to row B. Since the data is already latched in the row buffer, and the CS amplifier has a stronger drive than the DRAM cell itself, the data that is latched in the row buffer is from row A is going to be written back to row B. So we call this activate precharge command. So by sending consecutive activations to the DRAM row, I can copy one row to a destination row without the intervention of the processor at all. And this has really negligible hardware cost. So I didn't add any logic to do this computation. So this is just another view of what's happening when I'm doing this computation. So I activate this first row. As I mentioned, the charge, the cells lose charge to the bit line. This simplify amplifies the difference, and then the data is latched to the simplifier. And then I send another activation to the destination row, which allows the data to flow from this simplifiers to the destination row buffer. So we proposed this in 2013. It's called Mbit, and we see that by doing so, we can improve latency by 11 times and reduce energy by 74 times. And this is because there is no data leaving my DRAM chip. The data is still inside the DRAM chip itself. Since then, we keep doing several optimizations to the system. One of them is just a small optimization. So let's say I show that operation for inside the DRAM subarray. Let's say that we want to move data across the different DRAM subarrays, how you can do that, since there is no connectivity between the DRAM subarrays. And the answer is quite simple. We create the connectivity. So we use some isolation transistors to connect these amplifiers of neighboring subarrays. And this called LISA. This enables us to move data. I applied that same approach to move data across different DRAM subarrays as well. And then there are other approaches that we build on top of that. So this is just to do copy. So now I can copy one row to another DRAM row using this activate precharge command. Let's see what else can we do. So let's start doing some proper computation. So let's say that we want to support Boolean operations, so and or not and majority. All of these using low cost. So we are going to enable that by using the analog computing capabilities of the DRAM chip itself. By instead of activating only 2 rows, you're going to activate now 3 rows at the same time. And this is going to give some performance savings, and the same approach can be applied to other memory technology as well. So how this is working? So the key here is that this simplifier here in the DRAM chip is a differential simplifier. So if I activate 3 rows together, the 3 rows are going to perturbate the bit line at the same time, and the simplifier is going to amplify the voltage level to the majority of the voltage level of the other of the DRAM cells that I activated. So in this case, the majority of VDD, and ground is VDD. So this is going to be amplified to VDD. So basically, the DRAM simplifiers act as a majority gate when you activate several DRAM rows at the same time. So I already have some form of computation placed inside the DRAM chip that is in my computer or my phone. And by controlling one of these rows, I can do AND or AND operations. So if I set one of these rows as a control row and set it to 1, I can do A or B. And if I set it to 0, I can do A and B. So this is just to implement some algorithm to do that efficiently. Basically, since this operation, so when you do this operation, I'm destructing, as you can see in the figure, the initial input value of the source rows ABC. So I need to copy data. If you want to preserve the data, you need to copy this data to some reserve space using the row clone approach that I mentioned earlier. And then you can do the triple activation and copy the result back. What is missing here for this to be functional complete is a NOT gate. But if I look again to the circuitry of the DRAM chip itself, I already have a NOT gate there. This amplifier is basically 2 back-to-back inverters connected in a loop. So when I can redirect the output of one of these majority gates one of those NOT gates back to the DRAM cell using this N-word line here. And now I also can store data in a negated value. So now I can do AND or NOT. So if I can do NOT and then or I can do NAND or NOR, and then I'm full function complete. And this is just an example on how this is done. And we see basically significant throughput gains compared to other systems, and also energy gains when you're trying to do these operations inside the DRAM chip itself. We use this approach to accelerate some applications that do some Bitwise operations. Those are basically some database operations like bitmap index and also bitwave that I'm showing over here. So okay, I can do, hopefully it's more or less clear that I can do copy and I can do Boolean operations, right? But what about something more exciting? Can I do addition or can I do a major multiplication following the same approach? And the answer is yes. And to do that, we propose this SIM-DRAM framework, which we are going to do here is basically compose sequences of these triple activation, so sequence of majority operations, so that I can implement a circuit-like operation inside the DRAM to do additional multiplications. So this SIM-DRAM framework has three main steps. The first step, it takes as input operation that you want to implement using some logic gate representation. It can be Verilog, it can be some graph-based representation of your circuit, and it converts this circuit to majority gates only circuit because the main computation that I'm doing in DRAM is majority. And then it's mapping the inputs and outputs and edges of this majority not logic graph into sequence of DRAM row copies and majority operations. And then during the execution time, the user tell the application that he or she wants to use this new operation, and the enhanced memory controller dispatch this the operations to the DRAM so that I can do the computation as needed. So really briefly, I'm going to talk about those steps. So as I mentioned before, I can convert the equivalence between AND and OR gates to majority gates by setting one of the inputs. So if I have a representation of, for example, a RIP carry ANDer that only uses AND and OR, I can, or and not, I can easily convert these circuits to a majority-based circuit following this equivalence. However, doing this is not efficient because the circuit is not minimized. So basically, we use some tools from EPFL, some DA tool that takes this unoptimized majority not graph and generates an optimized version of the same graph. This is basically following like the Morgan's law, all of those things that we use for a regular Boolean circuit, and then we end up with the same equivalent circuit. And what this translates to when you're doing DRAM operations is latest improvement, because every single merge that you see in the left part here is a triple row activation that you do in DRAM. So if you can reduce the number of triple row activations, you're also improving the latency of the operation. So the first step is just generating this optimized majority not graph so that I can reduce the latency of the operation. So the second step, generate what we call a microprogram, which is just a sequence of DRAM row clone and triple row activations that implements the in DRAM computation that you want. So there are two main steps here: allocates the input and output for that graph, and also generates the sequence of DRAM comments for computation. The third step, so you do the first two steps offline and you do it once. So if you want addition, you do that for addition circuit. If you want multiplication, you do that for this multiplication circuitry, division, subtraction, so on and so forth. And then we store the sequence of operations that can, the second step outputs as a new ISA instruction. And then when the programmer wants to execute some computation, the memory controller translates the instruction into the appropriate microprogram and executes the computation inside the memory chip itself. To make this feasible system, we need to revisit several places in the computing architecture step for system integration, and we do that in this paper. But I invite you to check it out. So we implement this simulation, and we see that we can significantly outperform the CPU, GPUs, and previous processing memory architectures. So this is SimDRAM. So we keep working on improving this substrate because now we can do copy, we can do Boolean operations, we can do arithmetic operations, but there is a question related to the efficiency of the substrate. So in terms of programmability, so how is the programming model of the substrate? Something that I didn't mention before, but you might have noticed in the slides, is that when I'm doing a triple row activation or a row copy, I'm copying an entire DRAM row, or I'm operating an entire DRAM row at once. And a DRAM row in DDR4 chips, for example, has around 65,000 DRAM cells. So that's quite a big number. So how often you write a loop inside your application that you iterate over at least 65,000 elements and multiples of the 65,000 elements. We did some profiling of real applications, and we see that that's not that common, actually. Applications have a varying and limited amount of data parallelism that they operate over, but the processing memory substrate is not able to adapt to this parallelism, leading to underutilization. The second problem is that, as I mentioned, in SimDRAM, the user needs to manually search the instructions in the code to do computation. So you don't have a compiler, and this is quite this can create a problem. Sorry, this was the third step. The second step is the computation support, which means that I'm only limited to map operations. So I can do a vector plus another vector generating a third vector. But since there is no connections across your bit lines, I cannot reduce a vector into a scalar operand. So I'm limited to map constructs. And we did this paper. It was published this year in HCA, where our goal is to create a more flexible processing using DRAM substrate, which can adapt to the parallelism available inside the application and be more programmer transparent when executing computation. And this is called MIMDRAM, if my slide comes. Okay. And the main idea of MIMDRAM is to use this thing called fine-grained DRAM access for computation. So this is another view of a DRAM subarray. So a DRAM subarray is further divided into what is called a DRAM mat. And the DRAM mat shares this global word line. So when you access a DRAM row, the global word line is going to be activated across all of the DRAM mats, and it's going to bring all of the data from the DRAM row into the local sysamplifiers, the local row buffer. Even if the next read request is not for the entire row, it's only for a portion of the row, like a column. And this creates some energy and performance issues. And there are a bunch of work that tries to minimize this issue using this thing called fine-grained DRAM access, which the idea is quite easy. It's quite simple. We are going to segment this global word line so that we can only access the portions of the DRAM row that is going to be used later on from a column access. This is quite an oldish idea. There are several works that have studied that, but we are going to use the same idea for processing using DRAM computation, which enables with three main advantages. So the first one, I'm also whoops. Let's go on. My computer is thinking. Okay. So the first advantage that we get by using this approach is that I can only map, I can only activate the portions of the DRAM row equivalent to the amount of parallelism that you have in a loop, for example, when you're doing an addition. So if your loop only iterates over 32,000 elements, I'm going to only activate half of my DRAM subarray when I'm doing the addition, saving the remaining subarray, the remaining portion of the subarray for another application. So if I have another application that is data independent from the one that is currently being activated, I can execute that computation together in the same DRAM subarray, then improving utilization. So this is why this paper is called DRAM, because now I'm executing computation in that multiple structure, multiple data fashion inside a single DRAM subarray. And the second advantage is that I can use the local interconnect inside the DRAM subarray to move data from one portion of the DRAM row to another. And then I can implement reduction operations inside the DRAM chip. And finally, there is a nice property of these DRAM METs that they have the same number of rows and columns as the number of CMD lanes in modern AVX instructions. So we have 512 rows and 512 columns, and in your AVX instructions we have also 512 lanes. So we can map AVX instructions down to processing using memory instructions transparently from the programmer. So we are going to use these ideas of DRAM in both hardware and software, and I'm going to briefly mention them. So in the hardware side, I don't know what I mean. So in the hardware side, we are going to propose some simple modifications to the DRAM access circuitry so that I can activate individual DRAM rows, portions of the DRAM rows for the computation, and also some simple interconnection that connects the different portions of the IO, the global amplifiers together so that I can implement the reduction that I mentioned before. We're also going to have a more elaborate control units, the memory controller, to basically figure out which METs I'm using at a given point in time and which instructions I can dispatch concurrently. And in the software side, we implemented 3 LLVM compiler passes that are based on LLVM loop auto-factorization engine so that we can automatically identify code from loops that can be parallelized and might benefit from this type of computation, schedule individual computations properly, and then generate code for generated binary that runs that application. So we evaluate this system with 12 different applications from different benchmark suites, and we see that significantly outperforms the CPU, GPU, and prior processing using memory architectures in terms of energy performance efficiency. Then there is more in this paper. So here I mentioned that you can do using this new type of architectures, DRAM copy, Boolean operations, arithmetic operations, and means type of computation. But it's not limited to that. So we also look at some security primitives like DRAM unclonable functions, and also true random generations that basically operates in a similar way. Instead of activating 3 rows, we activate 4. And basically, the 4th one generates some randomness because of the sensing circuitry. And those are the works that is doing that. So to briefly wrap up the type of operations that we can do all of those, right? But we are still missing something. So I can, I'm not going to ask, but what I'm missing now is some way of doing some transcendental function. So I can do Boolean operations, I can do arithmetic operations, but what about a sine, a cosine, a logarithmic operations that I can approximate to using some arithmetic, like some coordinate functions, but is inefficient. And this in this paper called Mutlu that we did together with Gabriel here, we actually tried to mitigate this problem using our old idea actually, which is lookup tables. So all of these prior works that I mentioned before, they have this range of operations, but still they are limited to these operations that are more transcendental itself. So our goal is to extend the reach or the applicability of this process using memory operations to more arbitrary or complex functions. And as I mentioned, the key idea behind this tool is quite simple. So in a regular operation, you have your input ALU and the output, and you move the inputs to the ALU, it generates the function that you want. But another way of doing computation that's quite common in FPGAs is doing memorization. Right? So I store the possible outputs of the ALU in a table, and I change the computation to a memory access. And then I just do a memory lookup to query the computation. So we are going to do this in what's called a loop query operation. I'm not going to get into details on how we do that in the DRAM. Basically, we store several copies of a memorized function inside the DRAM subarray, and this gives us quite high throughput. But in terms of system integration, we implement some compiler and controller support, and also different implementations of this lookup table based architecture that has different trade-offs in terms of area, performance, and so we see that Pluto can significantly outperform the CPU and GPU, and also significantly energy itself. So I invite you to check the paper and the talks if you are interested. So you quickly to finish up, you might think that this is too futuristic or this is not implemented because I'm operating the DRAM chips in different ways that they were designed to. But actually, we have been doing some studies with commodity off-the-shelf DRAM chips. So these are DRAM chips that you use in my computer you buy in a regular store. They are not at all. And we haven't seen that actually by following up these ideas of digital automation, we can already implement some of the concepts that we use using those off-the-shelf.
Hello, Geraldo, can you hear me? Yeah, the problem is, I guess we cannot hear you anymore. Maybe your microphone's battery has died.
Can you hear me now, Girai?
Yes, now I can hear you.
It's a worse quality, but anyway, it's just I'm almost done. So so we can do functional complete this commodity off the shelf DRAM chips. I'm not going to spend much time on how this works, but I just want to give some intuition. So this is our testing infrastructure. So we have this FPGA-based testing infrastructure where we can modify the different, we can control, basically we have a custom memory controller where we can control the DRAM commands that we are actually to or DRAM under test. And also the temperature. So those are the chips that we check from two main manufacturers, SK Hynix and Hynix, and in total we check 256 different DRAM chips. So the way that we are achieving this different functionality is by violating the time parameters between different durable activation. If you just try to issue what row clone was like activates back to back, the membership does not allows you to it's not recognize that as a valid a sequence of comments. So you always have to issue activate followed by a charge and followed by another activate because it's how the specification. But if you violate the time that it has taken from between activate and upper charge, we see that the circuitry inside the direct chip does not have enough time to switch. So in the end, we are basically split this Chinese ignore, and we end up doing activate and followed by activate is what we need to do for our local operations, for example. And by controlling the locations of the rows that we are activating, we end up in different operations like open many rows, up to 16 rows, or up to 32 or 48 rows, or generating lots data of the input rows, or generating the majority of up to if we say 16 different inputs by controlling the data. I'm not going to go into details here. But yeah, so this is the main takeaway. So the main takeaway is that we don't need much to enable this. Actually, it's already enabled. We just need to the memory manufacturers to expose this to the software levels so that we can start like accelerating our applications and start doing this row copies or interim operations natively. So we also have some testing infrastructure available online if you want to test this type of systems called PyPyRAM. It gives also some software level APIs so that you can customize your software routine. This is the link. And it's quite easy to use. And we also implement some of those operations like the interim row copy. Yes, this example over there. So it's just to show that you can implement that as a system type of design. And it's available. PyPyRAM is available on GitHub, and there is some talks online as well. So yes, I already mentioned the clonable functions and random number generation. And just to conclude this part of the tutorial, this step of cross-computing memory operations are not limited to DRAM only. People have looked at doing operations, for example, in Flash or in non-volatile memory like PCM or VRAM. This is one of the oldest papers called Pinatubo that does that in PCM. And we have this paper called Flash Cosmos that does similar operations in named flash memory devices. So it follows a similar idea. You activate several rules at the same time, and you can do named operations. In terms of non-volatile memory devices, they have a nice property that are quite used right nowadays for accelerating neural networks, which is they operate a little bit different than DRAM. They don't operate based on capacities; they operate based on resistance. And when you are reading the data, you pass some voltage level through the cell, and at the end of what you have the output is the Kirchhoff law, or depending on the voltage level stored, the resistance level is initially stored in the cell itself. And basically, what you can do with this is a dot product operation in constant time, because if you look at the Kirchhoff equation in the left, this is basically a dot product of the voltage level that you put and the resistance level that is the cell. And a lot of some startups are actually using this type of memory devices to accelerate convolution in neural net tools because it's quite efficient. So this is another presentation on what is being done. And again, they are just mapping the inputs and the weights to the memory devices and doing the inference in constant time using this similar approach. So yes, this concludes this part of the talk. I don't know if there's any questions related to this process using memory architectures.
Question about it's more about them. So I saw somewhere that in module that spends around 20 watts. And I want to ask you, how does it compare with local GPUs?
The GPU of the GPU. So the GPU is much higher than 20 watts, right?
The power, yeah.
The power.
Yes, you have some GPUs that spend around maybe 10, 20, 50 watts. But the UPMM is 20 modules. And they have
total.
Total, yeah.
Okay.
Okay. And comparing also the number of cores, GPU and memory.
Yes. I didn't do the math, to be honest. So, and we have a physical access to their servers. So we don't know exactly what they're using for the cooling. But this is in the TCP of the server. That's also they are designing. So I guess they didn't burn the chip yet, basically. But the problem is that if you look at us, I don't know if you're looking at like the number of SM cores in the GPU versus the total number of cores in the memory system, but maybe you can look at the number of threads that you can execute because those cores are multi-threaded as well in memory chips. Each core can execute 24 threads. So if you look at the total number of cores, so in the system, 24 times 2000 something, and it's probably higher than the number of core threads that you can run in a single GPU, depending, of course, the size of the GPU. And if you do like an ISO power comparison, I believe that UPMM would be more power efficient for a given test. But yeah, again, I didn't do the numbers by myself, so I need to I will have to calculate to see.
I have also another
question.
In all of this, what is the role of the cache mechanisms? Is the vision for PIN systems to remove the cache and computing units inside the memory itself? Or what is the vision for incorporating these systems in modern?
Yes. So the premise that the big systems are operating on is that the application that you're accelerating is memory bound. And usually applications that are memory bound have low data reuse. And we did a lot of experiments in more than 200 applications to confirm that. And then since they have low data reuse, they don't make good use of caches or the features, even if you include the features. So usually we don't think about the systems with much caches, like deeper cache hierarchies, because they would not benefit. They don't benefit in the CPU type of systems, and they don't benefit as well in the APU type of system. So it's a bit would be a bit wasteful to put the caches over there.
So these systems will be more like an accelerator.
They are more like accelerator. They are not supposed to replace traditional systems because they are not necessarily like really compute intensive, but compute powerful. So they're, as I said, as you mentioned, the frequencies are quite low, for example, the cores are quite small. So they are not there to accelerate heavy-duty tasks, but compute bound, memory bound tasks. And those tasks usually don't benefit much from the caches from the beginning. There's another part of the answer for that, where there are people that look at as cache-based cross-linear solutions. So they put compute cores nearby the less level cache first. Because at some point, even if you have a lot of, if you have some locality, you might be bottleneck might move data, keep moving data across the different levels of the cache hierarchy itself. Although it's much faster than going to this route, it still is inefficiency. So they try to mitigate that particular move data movement overhead inside the cache hierarchy by doing computation around the caches. But it's limited because the moment that you need to go off chip, you lose. And then somebody you can need to think about the off-chip ones. So the way that I like to think about this type of systems is not like one versus the other. It's more like adding on top of what exists because, for example, GPU, right? A GPU by definition needs to have DRAM, or like it has some DRAM in it, right? Or your computer it always have DRAM, or I mean memory, some part of memory, right? So it's not. It's just equipping that main memory with some extra capability so that the moment that the GPU becomes inefficient because of memory boundness, I can go to that memory of the GPU and tell us that, okay, take over and do your thing. And I'm going to continue to do some compute bound tasks here. It's more collaborative than like one versus the other. Thank you so much. Okay, any other questions? Any more questions on YouTube, Girai?
No, we are all good.
Okay.
Thank you very much.
When you come back from lunch, we're going to talk a little bit more about the upcoming system. And some adoption issues as well for this. So hope you come back.
Yes, MD run. Can I? Maybe we can talk. Isn't able to use it.
That's it's not charged.
Does it work with you?
I don't know. Mira, can you pause the live stream?
Rakesh told me to keep it on actually. Should I click to?
So keep it on then. I don't know because we are going for like 2 hours. Like we're going to come back on quite late.
Okay.
If he said yes, just keep it.
Okay. I'll just put a PowerPoint screen now. What time are we starting back?
2:30. 3:30 Zurich time.
2:30 Porto, okay.
Qual slide?
45, acho que 46 ou por aí um bocadinho. Era antes dos 50, pouco antes. Era no majority.
I was also monitoring the questions on YouTube.
Hello, hello.
Hi, Geraldo.
Can you can you hear me?
Yes, I can hear you now.
Muito obrigado.
Okay.
Tá pior, mas vamos tentar. Vamos ver. Se eu chegar no final com voto, tá ótimo para mim. E das 3h30, Oscar tem posto. A gente pode começar já. Can you hear me from Zoom also?
Yes, we can hear you on Zoom.
Okay, thanks so much. And you can see the screen as well, right?
Yes, we can see the slides as well.
Great, everything's set. So welcome back to the story of memory-centric computing. Now we're going to talk about coding course. Now we're going to talk about process memory adoption and programmability. And if the time permits, we're going to go over the tutorial of programming. To be quite frank, I don't think we're going to get there. But anyway, I have to show the material if you want to go over it offline. So we're going to talk about, so in the previous sessions, we talked about architecture. Right? So we talk about this linear memory processing architectures where you're adding random computation, adding some computation here, the memory chips themselves, and processing new memory where we are using the memory cells themselves to do computation. The question that you're going to try to answer in this part of the tutorial is, okay, if we enable this type of different computation, different level in one architecture, so what we need to change if we're going to change anything, we cannot plug and play. What to make this computation efficient, what should I move in my system? And the question is, the answer is that we need to change a lot the current stack. So this stack is not designed, the computer architecture stack is not designed to support computation in arbitrary places across the system, right? Computation only has a single place, and everything around it, in terms of system support, is there to allow the computation to happen. So from the point of view of processing memory, we need to think from the very top of the stack to the very bottom of the stack. So we already kind of covered the bottom now. The top, it comes from application and software. So we're thinking of better ways of writing code so that we can exploit processing memory. But I'm going to focus more on the middle part in this talk here. So the middle meaning first, okay, if my program needs to write the code to do the computation, what type of code is that? What is the programming model that will be beneficial for processing memory? And what is the compiler support that I need to provide so that I can compile my binary to this processing memory architecture? And this also involves some system support. For example, now my data might be computed in two different places, right? Might be computed in the cores or in a different process memory cores in my memory. So how do I make sure that I maintain coherence and the consistency view across the entire system without penalizing performance so much? And this is the same problem with data synchronization, virtual memory support, isolation, communication. And there's also another question about, okay, I want to design, I want to project all of this to a future system. So what type of infrastructure I need to build so that I can assess what are the challenges and what are the benefits of this process memory type of architecture. So all of this can be done if you think first different from, or one step that you need to think different from one human architecture model, and if we go one step at a time. So we don't need to go and try to change everything at once, because that will be extremely complicated and probably will be also leads to an inefficient way, an inefficient system. But we can go and tackle each level of the architecture stack at a time and move forward. So in our workings in Safari, we have been slowly going through this stack, one problem at a time. Initially, we start very, very simple. We just assume we just assume that we have these 3D architectures, and these 3D architectures could do very simple operations, atomic operations like atomic addition, atomic subtraction. It is cross-memory architecture. It was in 2015, and a fun fact. So this was the main idea here is put some really simple functional units in the logic layer of a 3D stack chip, so you can do atomic operations over there. So you offload the instructions. And it's in 2015, and it was just announced recently, 2-3 months ago, that the next generation HBM4, the fourth generation of HBM chips are going to come with something actually similar to this. So the logic layer of the HBM chip is going to have, by standards, some computing capability that's lightweight and like quite simple as well. So it's really nice to. I didn't know that I was in a meeting with SK Hynix folks, and they were telling me about this. And I was really interested to see that, like 10 years ago, 29 years ago, these ideas might seem too risky or too future looking, but now, 10 years later, this is going to be actually implemented on hardware, so it's quite cool to see. So we also can think about easy programmability via software frameworks, so that the programmer does not need to think so much about the underlying hardware characteristics of the process memory system. And we have tools on that vein. And I'm going to talk a little bit more about the simple pin architecture framework that aids the programmability of a memory system. The main problem that you are trying to solve here is that programming a general purpose process memory system is quite challenging. So I didn't go too much details on the system, but basically the programmer needs to manually deal with several tasks, like distributing data across memory banks, managing data transfer between the host cores and the pin cores, and launching the computation, and etc. And this is because the memory system in particular is a loosely coupled accelerator. So you program this as program a GPU, for example. So you need to partition the computation, partition the data, move the computation to the P cores and start the computation. And to do this efficiently, a good programmer needs to know more or less the underlying hardware characteristics of the memory system, which can be cumbersome. So to try to mitigate this, we propose this simple P framework, which is a framework based on data parallel patterns. So we implement some common parallel primitives like map, reduce, and tip operation, and some communication primitives as well, like broadcast, scatter, and gather, so that the user can just interface with such primitives, and our framework handles the underlying code generation. So we implement simple pin for the memory system, and we evaluate the 6 different applications. Then we see reduce on lines of code, and we also implement some optimizations in the back end, and this is some performance benefits. And simple pin is open source, available on your GitHub. So that's the overview of simple pin. I'm going to elaborate on it a little bit more next. So I think I don't need to introduce the concept of processing memory system anymore. We're already familiar with this, but I want to introduce a little bit more the memory system architecture. So in the memory system architecture, and this is quite common across all the process memory systems as well, they can be abstracted away. So you have the host DRAM chip, your regular DRAM chips, and you have your process memory DRAM chips. And those are the ones that are going to be used for computation. But they are not going to be used as main memory. So you need to have two separate types of teams in your system. When you are going to launch the computation, you need to move the data from your host DRAM memory to the pin DRAM memory, and then you can start the computation. Inside a big DRAM chip itself, we have a DRAM bank. In each DRAM bank is 64 megabytes inside, and some pin cores, which are simple RISC-V like multi-threaded cores, and two SRAM buffers, instruction memory to hold the instructions, and also a splash pad memory that's called working RAM, that stores some temporary. Those, I think, just describe what I just said. An important property of the system is that it can efficiently support integer arithmetic operation like addition and subtraction. But other more complex things like multiplication or division or float point computation is emulated. If you have to do a lot of multiplications, it's actually not a good substrate. So how do you program the upmem system? So just example of how you do it. So upmem, the company itself provides a SDK, which you're going to use on the labs. And in this SDK, you have C-line programming models. It's quite similar to CUDA. And then the user is responsible for doing a bunch of tests. The first one being initializing some heap variables, allocating data in the scratch pad memory of the system. To do some boundary check, so making sure that you don't go out of bounds of that memory, loads the data from the DRAM banks to the scratch pad memory itself, then call the kernel that you need to do the computation, synchronize the several threads that are running concurrently on the peak cores, then merge the computation and get the data back from the memory to the processing memory cores. So this is challenging because, as you saw in the code, there is a lot of data management that the user needs to manually manage. So it's not just a CUDA run copy that you copy some CUDA data, some data from one memory to the other. You need to keep making sure that a particular GPU is only its own data, it does not go over boundary of the data. If you have to, so the data needs to be always aligned. We have this multi-thread programming model that you need to do inter-thread communication quite often. And if your code requires you to communicate across different memory cores from across different GPUs, the user is required to manually move the computation from do the synchronization from the host stack. So there is no inter-GPU communication. So any communication across GPUs, you need to do via the host, and the programmer is responsible for doing it using some primitives. So all of that creates an area for programmability, and our goal is to program provide a framework that can abstract away all of these properties from the programmer. And to this end, we propose a simple fit, which is this framework that's going to provide some API-like primitives that is going to encapsulate management, the interface, communication, and process. So it starts with management. So we include some metadata that is what the user is going to indicate. Going to use to indicate that a particular array that you want to operate over is an array that is going to be operated over on the processing in memory cores. So you think about this as just registering array as the this array with a given size that I'm going to later on offload to processing memory core. This is important because as I mentioned, as is implicit here, in the same code you might have code that you execute on the CPU and codes that executes on the peak cores. So you need a way of distincting which the instructions are executed. So you have to look at them to retrieve some relevant information about the array. So the size, the base data structure that is used, some API to register that array as a data structure that's going to be used for processing memory computation, and also a routine to just rearrange. So you can think about all of those as specialized models. So then we have the communication interface. So there are three main types of communication that you do in the PMM system. The first one is broadcast. So you want to transfer chunks of data from the host CPU, the host memory, to across the many DRAM banks that we have across the processing chips. So this API is going to encapsulate this routine. So here I have an example. We want to transfer all of the data 1, 2, 3, so multiple copies of the same data across all of this the neural nets at the same time. So it's just a broadcast. The second one is the gather operation. So I'm going to move to the figure because it's easier. So in the scatter data, you want to scatter some pieces of array across the different neural nets. In the gather, you want to connect some different pieces of array and merge it together to create a different a single array in the host memory. And for that, again, we have some APIs that encapsulates that input. The third one is the reduce primitives. So here, what we want to do is reduce all of our array based on some operation across the many DRAM cores in the PC system. And this is quite useful for synchronization routine, where we have, for example, a shared memory space that you're using to as a synchronization point. So they also have the opposite of that, which is the I mentioned the our reduced, and the other one is altogether, which is combining a pieces of data from array and distributing that piece of data to the processing memory cores. So the third step is the computation itself, the computation pattern that you're going to execute. And as I mentioned, we are based our computation patterns on data parallel patterns. Map, use, and zip. So array map basically defines a function that you're going to apply to all of the elements inside the same inside that single array and producing an array. So you basically register that function that you're going to use, and the function can be anything, can be addition, can be histogram count as needed. The reduction, of course, is collecting, is reducing input array based on some access function and reducing that to output array of potentially smaller elements as an output. And the accumulation function basically accumulates the output values into the output array. And finally, the zip input function is going to take two input array and combine them into a single output array. So all of those parallel patterns, they might sound a bit abstract at this point, but they are quite good when you look at parallel programming, and usually parallel programmers are used to those primitives, at least they get scatter type of execution model. People have shown in the literature that you can express a variety of algorithms just following those data parallel pattern primitives. So that's why we implement those three. So we also implement some, when generating the final code development, we also implement some optimizations in the backend, so we can hopefully gain some performance. I'm not going to talk much details here, but we have things, for example, as loop unrolling. So since arithmetic operations are costly in this memory system, things simple that you are not going to optimize for in regular people, like unrolling, minimizing the amount of time that you increment a loop counter, is beneficial to accelerating the memory system itself. So we do some loop unrolling so that we can have to iterate fewer times. A loop counter. I will do the same for function in mind, so that we don't need to go to memory to fetch some particular function, and some adjustment to data transfer size and for more detail, let's check. Okay. So we implement single pin in our real mapping system with more than 2,000 pin cores, and we use a real benchmark suite from a benchmark suite that we actually implemented called Prim. Those are quite simple ones with reduction, but we have some more complicated ones like linear regression and logistical regression. and we compare to a optimized implementation of those algorithms. So that's just an example again from the same code that I showed earlier for the histogram that is using the optimized version for the algorithm codes. And what I'm going to show next is the equivalent implementation using simple. So basically, the program needs to do is define the function that we want to execute, a access function for the reduction, the mapping of the inputs, and then create the handles to store the outputs and do the scatter data transfers. So in terms of line of basically code. So basically, if you look at just how much less crowded it is compared to the other, could have idea of how such type of frameworks can improve programmability. And if you use lines of code as a metric for programmability, we see a significant reduction in lines of code for those six application compared to the optimized, the end optimized. So it's from about 3 to 6 times reduction in lines of code. So we do some weekends from scaling analysis for those workloads, and we see that we observe comparable performance to any optimized code, and sometimes even some performance gain because of those optimization that I mentioned that we do on the back end to hopefully improve performance. And a similar behavior for the strong scaling. So right now, theme is designed for of them like cross memory systems. But we think that this type of system can be further extended to other process memory architectures like the Samsung one, for example. So what we want to do in the future is to improve the communication between P cores themselves, because right now the way that the framework works is by emulating the communication between P cores and the whole system. You also want to, we are looking at implementing more data parallel operators that can be used for other applications like prefix sun and Celsius for convolution, and also some parallel operators that enables random access because currently it's quite hard to support. So this was Kupima that is available online. I'm not going to go to the conclusion again because it just concludes. Is there any question related to this framework?
I have a quick question about the implementation itself. When you implemented the scan and gather packages and all those operations, did you use the same interface as NPI? So the same order of arguments?
Yes. So I'm trying to make it as intuitive as possible. Okay, so this was one way of that we are trying to deal with this programmability issue for process memory, but there is also a lot of other issues, that, for example, as I mentioned, maintaining data coherence, right? So what happens if two P cores, if a P core and the host cores try to access the state memory location at a given time? And then basically what we saw that if you just deploy traditional coherence algorithms like MOESI or MESI approaches to and throw it into the system, we lose a lot of performance gains that you can get from the process memory system, because coherent traffic is quite quickly. And then we basically implement this new algorithm called lazy for coherence for proximity cores, which is based on speculation. So you let go the host core and the host system and the P system and access data at the same time, and you keep a map of the writes that both of them did. And every, after some parents these writes, and you check if there is an intersection, and you roll back those memory addresses. I don't know what happened to my screen. Oh, sorry about that. That was good. So we also look at other things like synchronization primitives for this was in particular for was on the for the QFP system, but a similar type of system, and also how to support, for example, virtual memory, code and data mapping, and also it's quite important to figure out which applications are good candidates for this type of system, right? Because this is not a Swiss knife type of system. So you need to understand what are the properties of the application that can indicate if you should upload that application to the systems or not. So this is my first preprint safari actually called DAMU, which is a methodology and a benchmark to identifying application property of the application that can tell you to upload or not on purpose. The main we are coming from a point where we knew that processing architectures are good for memory bound systems. But this metric, this thing called memory boundness, it's really hard to define actually. So what does it mean something to be memory bounded, and how memory bound something needs to be so that it is worth it of loading the computation for processing memory systems. So at the time, what was common for people to do was either to use a roofline model or use the level cache API metric from an application to indicate whether or not you should upload some computation to P. So we did some analysis to saw how good that approaches were, and we saw some interesting things. So here, for example, we have the roofline model. It's a quite popular model to tell you if some particular application is memory bound or compute bound. So here in the x-axis we have the arithmetic intensity of application operating provides, and the y-axis we have the performance of the application in gigahertz. And then we have two rules. So the first rule it equals to the peak system throughput, peak arithmetic throughput that your architecture can support. So it's the property of the system itself. And if application lies below this line, the Rhodes rule, we say that the application is compute bound. So the second rule is called memory rule, and is equal to the maximum peak bandwidth of your memory device times the arithmetic intensity of your operation. And if application lies below the memory rule, we say the application is memory bound. So people were using this approach to decide whether or not to put something to process memory, and we did the same. So we took around 144 different applications from various application domains. We plot them in the roofline model, and we compare also its implementation to process memory version of their implementation in terms of performance. And we saw something. So we have some applications that run always faster on the CPU cores, some applications that were always faster on the NCP cores, some applications that have similar performance if they run on the CPU or the NCP cores, so pretty much the same, do I have a preference, or the performance depends, and depends on different scaling metrics, like how many cores you put. So we see some interesting results. So we saw that as expected, application always there was some applications that were memory bound, and there was always running faster on the process memory. We also saw some applications that were compute bound and was always running faster on the CPU core. But actually, there was quite a good cloud in the middle from, for example, applications that were memory bound. But when you look at the performance was actually either faster on CPU cores, so they were memory bound based on this definition, or its performance would depend on how much power we put to the system, how many cores we use. And the same happened for compute bound applications, where we saw some similar performance between the CPU or the NTP cores, or again, that performance would depend on some system properties. So the main takeaway here is that even though the offline model is a good first indication of something, if something is bound by compute or by memory, it's not one type fits all methodology to indicate if something would benefit for cross memory or not. The second thing that people were using a lot around this time to indicate if something would benefit from ping or not was to just look at the level cache miss per kilo instruction metrics from application. And there was a magical number that there was in many papers that said if this metric is larger than 10, the application is memory density, then it's likely that it's going to benefit from processing memory. So we did the same analysis for those applications. The y-axis here, the x-axis we have the less level cache PKI, and then the y-axis we have the speed up that the processing memory cores was provided. And then we saw that, yeah, the applications really high in PKI often were benefiting from processing memory, and application with really low in PKI was benefiting more from the CPU core. But we also found some applications that were in the middle, applications with low PKI, where the performance will be either faster on the NDP core, the performance will be similar to the CPU core, or its performance would depend. So we conclude that this metric alone is not enough to indicate again NDP suitability. And the overall conclusion is that we were lacking a methodology that can comprehensively tell you what's the type of data movement bottleneck that your application will be facing, and correlate this type of data movement bottleneck with most suitable data movement mitigation mechanism. So our goal is basically to design this type of architecture. And to do that, we designed this three-step framework called Move. So it takes and puts the application and application binary. And in the first step, we use some other profiling tools just to isolate the functions of interest for us to study more details. That is completely optional if you already have the function that you want to investigate in mind. And then we create some simulator that allow us to understand based on the memory trace how much the locality that function has, and some scalability. Sorry. Oh my gosh. Why is not charging? Okay, let's try taxonomy. So and then it runs some scalability analysis to figure out what would happen if you change some system properties of the application. So based on this analysis, we end up with some different 6 classes of data movement bottlenecks that would depend on the evaluated metrics. So the first step, as I mentioned, we went to just to identify some functions that might suffer from data movement bottlenecks that are filtered, because we look in this work, we look at initially 300 different applications from various domains. So it's a lot of applications, a lot of compute sets, and each application has a lot of functions. I think in total in the end, we look at 77,000 functions collectively across all applications. So we need to have some sort of first level filtering to indicate which function we would conduct further analysis on it. And for that, we use this metric available in the Intel Virtual Profile called memory bound, which is defined as the percentage of the CPU pipeline slots that are stalled due to load and store operations. So in the second step, we want to understand what are the fundamental data properties of that memory access of that application. So we are looking at metrics that does not depend on the system. So those are basically how much spatial locality and how much temporal locality your application itself has or possesses. To do that, we use some frameworks that provide some algorithms for you to quantify spatial and temporal locality from a value from 0 to 1. So for us to calculate the spatial locality, we trace the application access and we see how many strikes we have. So if the application only always access the next element in an array, the stride would be always one, for example. So you could be incrementing the stride one several times. And then based on that, we create what's called this stride profiling history, where we put basically as the means the stride that we observe how the means indicates how often those strides happens, and then we get the cumulative distribution below this histogram, and this gives you a normalized value from 0 to 1. So value of 1 indicate the application has really high spatial locality. So this is the application that is constantly accessing the next element once after the other. An application with 0 spatial locality, if you think about this structure profiling being all around, so it's like a random access. We also have a temporal one way of calculating temporal locality, and this is easier, just very much with what's called reuse profiling. So how often I see the same memory address repeated in the application, and again we calculate this reuse profiling histogram and get the cumulative distribution below from the histogram itself. And then this gives you a value from 0 to 1. And an application has high temporal locality, a value of 1, if you keep accessing the same address all the time, or a value of 0 if you or rarely access the same address twice. So the third step, we want to look at more system level metrics. So the first step you're looking at, the second step you're looking at the application, and in the third step you want to look at the system. So we collect some metrics. Two of them are already from Fireworks, arithmetic intensity, which shows how compute intensive application is, and also the level cache, misperfilling structure, which tells you about the memory intensity of the application. But we also produce a new metric called LFMR, or length to first ratio, which is the ratio between level cache miss per L1 miss. And it shows the how good the application will benefit from a deep cache hierarchy. So this gives you also a value from 0 to 1. So if this value is 1, for example, it means that every time that I have a miss in L1 cache, this miss is also going to be a miss in L2 and a miss in L3, and I need to both change. A value to 0 means that mostly miss from L1 is being featured in the L2 and L2 caches. And why do we look at L1 here in particular? Because usually processing memory chips have at least one level of cache hierarchy, for example, as the working RAM that I mentioned before. And this is quite common across memory cores, because at least some degree of spatial and otherwise you have to keep accessing the DRAM memory, which takes time for every single request. So based on these metrics, we did this memory bottleneck classification analysis to try to identify when you are scaling the system. So the number, when you scale the number of cores in the system, you are putting more pressure in the memory subsystem. So we are exerting much and more pressure in the system to a point that is saturated. Then we can look at the state of the system. When the system is saturated, those metrics are having these values. And then we can also compare this whole CPU system, saturation of the whole CPU system, versus a memory like process memory system, where we have So simple cores together with some simple general process cores together with some L1 cache connected to a high bandwidth storage. And just as the simulator is available, and the benchmark that I'm going to mention later is available. So I'm not going to go through every single detail on the analysis here, but basically after we did this analysis for more than 100 applications, we could cluster and all of the data into 6 different classes of data movement bottleneck. So those are something more obvious, like applications that are durable bound or applications that are durable bound. But you also have some classes of data movement bottleneck that are not so obvious, like applications that are bottlenecked by the capacity of the private caches, or applications that are bottlenecked by cache issue, either because of coherence traffic or because you have many threads everything data from previous caches all the time. So all of those different threads correlate with also different data movement mitigation mechanisms. So some of them benefit from deep cache hierarchies, while the other ones do not, or some of them benefit from PIM, while the other ones do not benefit. And again, this is online, and also the workload that we use for this, and also available. So this is the move system. So is there any question related to that move? So okay, so I'm going to conclude this portion of the talk for going to the programmability. So basically, the challenge that we have for future systems is that we need to look at we have this opportunity to look at more fundamentally energy efficiency and performance computer architectures. If you think about moving data the least amount of time when you're doing some computation. And for us to do that, we need to design more intelligent systems that are data-centric, data-driven, and data-bound. By enabling computation near the memory, this can provide us to order of magnitudes improve in terms of performance and energy efficiency, enable new application and computing platform better, and this can further allows us to have better understanding of the universe or the things that are around us. Right? So the future of this memory computing architectures are quite bright because now we are seeing them realize further and further into the industry. So people are actually looking and are actually interested in this type of architecture, which is really good because then I'm probably going to have a job after. So this is this conclusion that we need what is creating a barrier for this to fully be adopted in your regular computer is this computer architecture stack, but we can go through it one step at a time if you think in a more open-minded way. So again, all of what I talk about here is based on this book chapter that we have online if you are interested on a survey of this cross-memory architecture. We also have a bunch of lectures and webinars available in our website. We have cross-memory, we have a class in dedicated only on cross-memory architectures. Everything is available online. I have several of those tutorials, the computer architecture conferences. It's really hard. And we have one that's going to start next week in Buenos Aires, and we also live streaming it if you are interested on checking it. So yes, we have much more resources online, and this is the part of the adoption. And then I'm going to move for programmability before, if the times allow. I have a little bit of time. Okay, So it's going to be about programming the memory system itself. It's not a general view of programming many process memory architectures. So before, I'm going to give a more detailed view of what the architecture that you are dealing with here. As I mentioned before, I already mentioned, showed this picture and this system where we have the CPU, the regular drum names, and the processing memory teams together. And this entire system, that you can rate from up there, you can get around 2,500 different cores.
Speed. Those are USB ports on the DIMMs.
Yes,
Debugging or
it's for debug. So, and a lot of the materials who are interested in the operating system is based on this benchmark that we did for the from the when they were releasing the Philippine course. So this is the initial patent that Fabrice is the I guess the main idea of the architecture, the patent that they filed before releasing the architecture itself. So you can see here the descriptions are quite abstract. I mean, having a memory array that has a processor put on it, other than the central processing and this processor detects the memory bank itself, and this is the view of what it detects. So you have this a method interface together with some wave interface here. So the memory array together with the instruction cache and the working memory. And then also the support. So overview of the operating system. So all of those are based on DR4 Durham teams, and those teams are organized on ranks, and a rank has 8 or 16. So I think that 8 or 16 Durham teams, depending if it's configured with 1 or 2 Durham ranks. And if memory chip has 64 megabyte DRAM bank called M1, so main one, and 8 DRAM processing memory units, so 8 DPUs in each chip. So in total, we have 64 of those DPUs per range. So this again comes from the initial patent that they filed. So here are the big chip, and then inside the big chip you have the memory, the main RAM, the SRAM ones, and the which is the working RAM, and also the DPUs. So inside the GPU, we have some interface for control. We have some DRAM engine that allows the cores to the GPUs to access the DRAM engines without a specialized memory controller. So the example is here this DMA engine. We also have the structure RAM that's going to store the program that you're going to execute, and 54 kilobytes working RAM, which is a scratch pad that's going to store the working memory that you're going to use for computation. So the core itself is a really simple multi-threaded core with 11 pipeline stages. So about them here. And they run at quite low frequency, 455 megahertz. So those cores are, as I said, threaded, and they can run up to 24 hardware threads to model the pipeline stages of this. So briefly, introduction of fine-grained threading. This is a quite old idea implemented in processor, which enables the hardware to keep a different context. A context here is basically a PC of a program plus offset of a register, and then at every single cycle that the core takes, the core fetch data from a different PC plus register from a different PC. So this basically fetch from a different threads. So this enables you to have several threads executing together in batches. Hopefully, if you want to install, you don't install that thread, you go to the next one, the next, so you can have and also you don't need to include some fancy hardware to handle data dependencies within it. So again, it's quite just a reference. It's what I did. It was implemented in the systems or there's a list. Onur has a lecture on 5 variables. So yeah, so the Memory system implements this, and the instruction set for this core is also quite so those are 32-bit instruction, which are mostly targeted scalar operands, and the implement people also implement LLVM compiler that is used to generate code for this architecture itself. So that there are more on the organization. So as I mentioned earlier, for you to program the implementing system, we need to think about accelerator execution model, because even though that would be possible to implement a more technical accelerator where you don't need to copy data from the host human memory to the DPU memory, that would incur some challenges that I guess the people don't want to deal with right now. So that's why they end up with this accelerator model. So basically, the DIMMs, they coexist together with regular memory DIMMs, and when you do before you do any computation, you need to split the data between the memory processor and the accelerator itself, and this is also launch the camp. And this is very similar to GPU programming, as I mentioned earlier. So this is the abstract view of the GPU programming. So those GPU programming can be split in 3 main steps. First CPU to GPU data transfer, so then GPU core execution, and then the result remove back from the GPU memory to the CPU memory. So you're going to do pretty much the same thing over here for the processing memory cores from GPUs. And again, it comes from the pattern, and as you can see, it's pretty much what I just mentioned for the GPU memory. You load the data from the banks, then you do the computation, and then you move the data back to the host CPU. So is there any question about the architecture itself? Okay, if not, I'm going to start through some simple programming examples, and the goal here, you're going to just program a simple vector addition computation. So I have 3 vectors. So one output, I want to compute A plus B, so the 2 inputs A together and put a third output. So based on that paper that I mentioned, that we benchmarked the processing memory system, we did a bunch of general programming recommendations and takeaways, which I'm going to mention later on when they are required for computation. So again, the computation that we are going to do here is quite I have this 2 already, and we want to add them together in a sort of way. And the first thing that we need to think about is how we want to partition the computation. And the partition here is going to be quite simple. So first, you're going to partition the input array across the different GPUs that we have in the system. And then inside the different GPUs, you're going to partition the computation across different threads. And in the upname nomenclature, we call the thread tester. So basically, first partition across the GPUs, and then you partition further the computation of the GPU across the different threads. And a good resource for you to understand how to program the upname is, of course, the SDK documentation that they provide online, and or that they have more description of those. So in terms of programming recommendation, the first one that we do is that for you to achieve high utilization, it's better to execute that much computation on the GPU cores as possible, because you're going to have some latency overhead of copying the data from the host CPU main memory to the GPU main memory, so you need to amortize the cost. Again, it's quite similar to what you do with GPUs. The second thing is to try to split the computation into blocks that can be executed independently as much as possible, because there is no communication, there's no way for the GPU's cores to internally communicate. So there's no inter-GPU communication that will support. So any communication across the GPUs needs to happen through the host, which generates more latency. So the second one, the third one is to use as many GPUs in your system as possible. So the latency of operation for the GPUs is quite good because they're running low frequency, right, as I mentioned. So you want to throw as much throughput as possible to the problem so that you can high-locate this. And the fourth one is to use at least 11 test nets per GPU, so 11 threads. And it is because you need to fill up the pipeline of the GPUs, which has 11 stages. So for the SDK, implement several different APIs for you to manage the UPMP system, and I'm going to mention some of those APIs. So the very first step that you need to do when you are implementing code from UPM is to allocate a set of GPUs that you're going to execute. And to do that, use the GPU alloc API in the number of GPUs that you're going to use, and this returns to a struct called here is the label GPU set, which stores those allocated GPUs. So you might you allocate different GPUs on the execution of the program. Basically, they say yes. We will show example next, and you allocate the GPUs with GPUs. So there are some algorithms. For example, this is a bioinformatics algorithm for DNA sequencing, where the main computation is executed using dynamic programming. As things we are executing the computation in dynamic programming, the number of computation increases and increases as the computation progresses. So you need to allocate the GPUs as you go during the computation. And basically, what we do here? So we have this for loop, like the main loop of the matrix of the dynamic program that we're executing, and we keep allocating and freeing the GPUs as needed, doing the dynamic program steps of the computation. So the second step, so after you allocate the GPU, the second step is to load the binary into the IOM. And to do that, you basically use this GPU loads API, which you pass the GPU binary name of. So you might can you launch different kernels into different GPUs in the execution of the program, and that's possible. And it enables that different type of parallelism model at thread level, which is test level parallelism. So you can have different programs using different GPU sets at the same time, and across all of those 2,500 GPUs that I mentioned earlier in this. Then you need to transfer the data. So you have two types of transfers: CPU to GPU and GPU to GPU. CPU to GPU and GPU to CPU. So there are three main transfer APIs that the main SDK provides. The first one is the serial API that allows you to target a single GPU. The other one is a parallel API, which enables you to use a parallel transfer to call several chunks of data across several GPUs at once. And the other one is the broadcast, where you're going to copy a single piece of data across several GPUs at the same time. So to use the stereo transfers, we use the GPU copy to and from depending on the direction that we're going. So this is just an example here from the parameters that you might use to copy the data to and from. So we need to pass a heap pointer that points to a piece of data in the RAM that is freely accessed to the application. but it's not allocated in specific location. So that's just some definitions of the parameters of the arguments of this function. So this includes the C2 pointers, every type the dual lengths that the data is going to be copied to, the pointer in the memory, which is the source of the data, and the size of the buffer that you are transferring. The second one is the parallel transfer. So here we're going to copy several buffers together, several DPUs at the same time in one transfer. But the caveat here is that all of the buffers needs to be the same size. So for that, we are going to use two different APIs, DPU prepare aspects and DPU push, and they also have the direction if it's from or to. And similarly, you have to pass the pointer to the memory, the direction, and the offset inside the memory and the transfer. Then you have the broadcast API, which is basically broadcast the data from CPU to the DPU and broadcast the data to all of the DPUs in the DPUs. So here again, we have to pass a pointer to the memory where the source of the is, and then the transfers. So so you can have several different types of transfer in the same program. This is just an example from select benchmark suite, where you're going to have some broadcast transfer, so parallel transfers in the beginning, and then some serial transfers from the end to pick up the data from the output.
I just have a question about performance, and it's not clear to me what performance, just note here, and what's the performance method that you use to monitor when you are loading and running different carriers, for example, on multiple GPUs for this.
From the execution time.
Yes.
So for what we basically use, because we have a task to execute, right? So let's say it's one algorithm, like the select algorithm that I mentioned here. So the end-to-end execution time that you are actually measuring. And then the handout you're going to see that we actually implement some counters to just count cycles and also to count time, and then we just measure the time it takes for different portions of the computation. So the main metric is just time, either in the second.
And how does it influence further other optimizations? For example, if you have execution time, just as you said, and I have other levels of your research, how does it influence each other?
So as I don't know if I fully get the question, but we basically just want to minimize the execution time as much as possible. And another metric that we use to combination execution time itself is called parallel speed up. So basically is how if you do the computation using one core and we start adding cores, how much faster it gets, and then we start seeing how it scales. And then at some point, the scaling starts to saturate or even going down. And at that point, you need to actually look at the problem and say, oh, just train more cores here. We need to either be smarter on software and optimize it somehow. Or we need to modify the hardware because there's a bottleneck that we need to mitigate. So I guess that's how the metric guides the research in that direction. So for growth like saturation.
I was just imagining the kind of application that I work with, like energy consumption, like when you speed up execution time, you have some energy consumption. Let's just optimize some in all applications.
Yes.
So I'm just imagining how I can set up one another with these transfers. Is that even
so this transfer is not going to tell you much the trade-off between energy consumption and but it's not the goal of that function as well to give you the trade-off. Like that's the goal of the performance modeling engineer doing the analysis. In terms of energy consumption, it's important for us to remember that the initial slide that I showed earlier, that if the alternative of doing computation like this, with the computation in the whole CPU core, like the regular system, where probably I'm going to move more data across the entire hierarchy compared to the computation like this, where the core localized. I think that the energy for those applications are quite simple. The computation part is quite cheap in terms of cycles or in terms of power. Then what dominates the execution, the energy consumption here is going up cheap in moving the data. So if we can make that data movement is smaller and smaller, and is what we are doing here with the system, that time is going to improve together with energy savings. So they go hand in hand together. Of course, if you try to push a problem that is not a memory bound problem into the system is going to stop, because if you break down power time, you break down energy, you're going to see that the majority is coming from proper computation, and this data showed that the frequency of the score is quite low. So it's going to take a long time for you to do something, and as you know, the longer the time takes, the more energy it's going to cost you. Yes, it's quite problem related. Yes.
So it's probably the programmer's responsibility to decide the size, the best size of the chunk.
Yes.
Not to point the branch
as much as possible. Yeah. So I did this. I should have done this more often, because what people been trying to figure out by themselves, actually, and what I mentioned earlier, that's failing. Because there is no, like, usually if you look at API, they have several different sizes of transfers for different use cases, and there is no one that fits all. It highly depends on the application. So it requires some time exploration for you to figure out what's the best one for a given task. The same as the
compatibility would be another issue of different use.
Compatibility with the
compatibility issue, like when deploying the binary have different views, it would be a headache process.
So here we don't have heterogeneity in the hardware. So you only have one type of hardware. But this is because this was just released. So UpMem is about to release a new version of the same architecture. So heterogeneity is going to start being introduced, and then it's going to start creating problems. Okay. So I lost track what that was. So I mentioned this already. So if you want to communicate across the different DPUs, there is no communication path. And this communication path is handled by the host processor. So we need some profiling to figure out how fast those data transfers that we have are. So we did two experiments. The first one, we use a single GPU, and we vary the transfer size from 8 bytes to 32 megabytes. And then we have one rank with 32 with multiple GPUs, if I'm not mistaken. No, 64. And then they have a fixed amount of data that you want to transfer, and in the same rank. So what we saw is that this transfer is actually bottlenecked by the DDR4 channel that connects the DIMMs to the processor itself. But at the same time, this cost of this transfer needs to be amortized if you do enough computation. And again, same as GPUs. So this is just the result of the experiment that I mentioned. So here we have the y-axis is expected to stay in the transfer side, and as you can see at some point the GPU transfer saturate, and the same for the GPU to CPU transfer. So all of these basically is to show that you need to have enough transfer size so you can reach to the peak utilization of. So across the rank, you see a more constant bandwidth latency. So this is the first one. Is the serial transfer, and in the iteration one are the parallel transfers. So the takeaway here is that the state bandwidth increases if you are using more distributed inside the same because. So two more observation here about data lightning. So I want to briefly talk about property of this particular type of system, and which is about transposing. So in the current DRAM chips, if you have a cache line or a word that is 8 bits, and you have 8 DRAM chips, your system is going to spread 1 bit per DRAM chip. So when I read data, I can read all of the chips at once, and then I can improve throughput, so improve by utilization of your system. However, for this chip, memory chips, I need to keep a word this 8 bits of data or cache line inside a single CPU chip. I cannot render it across the different DRAM, the bits from a single word across the different DRAM chips. But the whole that because you don't do it, you run into performance issues. So the Memory-Centric provides some sort of transposing engine, which reads the data in this distributed bit fashion from the host CPU, from the host memory, group the words together and dispatch them in a localized manner to the same different chips. So this enables you to have the correct data, but at the same time, it incurs some extra data, some extra overheads for the computation. So you need a bunch of micro benchmarks to characterize the CPU communication and so on. If you want to run your case, your GitHub. After you manage all of the data transfer, you just need to launch the computation itself from the DPU launch kernel from the DPU set that you're going to execute. And later on, you can use some synchronization primitive to wait for all of the DPUs to finish. So basically, so this is just some idea that you can use the synchronization to improve task algorithms and others. So finally, if you want to set parameters, input parameters to the main system, and parameters that will spec here the worker itself. So here is the example. We have this input elements in the array, and we are passing and using the CPU cop to or the CPU push transfer with the parameter that you want to pass. So we call that the traditional example that I mentioned earlier, putting everything together to do the execution of the computation. We have this. So first, similar to what you do in CUDA, where you get the transaction, you also can get the template ID for a given computation. So we have the size of the data that should be processed or fired by the single DPU, the transport of the data from the DRAM bank to of the input array to the working RAM and use the proper data transfer, the launching of the kernel itself, and finally copying the data back from the working RAM to the DRAM, the M. So the code for the vector addition is quite simple. Just a vector addition. So we don't need to worry much about that. So you also have to think about synchronizing the different DRAM threads using the available primitives that the Memory-Centric provides. So those primitives are basically input text ancient areas and then primitives. And this primitive just let them all you use that to do a parallel reduction. So you want to reduce a range by scalar vector. So you first allocate the GPU and then different test class inside that GPU itself. And each that class is local stuff. So it's an example here of the code that I just mentioned. It's going to use accumulate variable to accumulate the glucose sum here. And then you're going to use that class to the final reduction by using the variable weights primitive. Yes, so this is a nice way of doing vector reduction, where you're basically implementing a reduction tree. But you can do it in a more in a smarter way using the length of that, because if you do that, your synchronization is going to create a perfect bottleneck. But you can use other type of reduction that protects some base reduction. We minimize the amount of synchronization primitive for computation. I'm not going to get detailed on how it's here. And depending on how you manage the computation to different different inclusive for expectation. Want to get to the tutorial part before time finishes. And so if you do that, there's more reduction data because you're using fewer synchronization. So there we have a lot of more comprehensive lectures about programming, and we don't have much time, and I don't have much voice. But there is a website for this tutorial online, and over there is a handout. If you have a program development system, you can follow this handout here, and there are some important to guide you to exercise using primitives, computation. In the part for primitives, you don't have to have you access to the memory system to do the training out, because the memory SDK provides some simulator and put that Docker container with the simulator already stored just to fetch Docker and run it everything up. And then you can already play with the programming models, so you can see the programming model without having points from the memory system. So there is four main tabs and two templates for the tab over there. So the first step is basically the data parallel transfers that I mentioned and measuring the latency and the curve on this side and how much the dominant views it uses. And the second step is to implement a simple kernel XP that's y equals y times alpha plus times x. And it's basically a little bit of a more complex version than vector addition that I just mentioned. And then again, that's need to modify that same kernel to for you to see what is the impact of the latency of the views, different data structures or different data types. Because as I mentioned, the ALU of the CPU is quite low. So if you go to higher destination, for example, your throughput is going to decrease. But if you go to multiplication, your throughput is going to decrease. So on the code there, the big file, you can change the data type. So it's the handout. And then to exercise the different areas of the reduction using the different correlation. So the handout is the website that I just wrote that but I can fit quickly in case you want to take a picture.
It's the Heart website.
Yes, I don't know if it's linked on the Heart website.
Yeah, it is.
Great.
Heart, World, and Memory-Centric computing systems.
Great. That's perfect. So yeah, if you go here, the handout is there. And you can follow by yourself. If you have any question, let me know. And there's a bonus one for RDP conversion. The material should be self-contained, so you should be able to exercise this by yourself. I'm going to put the link of the handout here just in case. So I don't know if there is, I think you just have still 5 minutes left. I don't have much voice left, but I can try to answer any follow-up questions that you guys have. I don't know if there's any further question on. You can try the tutorial as well now. If you want, I'm going to have to use to catch up on it, but I'll be glad to take a question.
You showed you were talking about the answer.
So it's following up the handout. Yeah. So everything explained there. Yeah, thank you. Is there any other questions?
Sure. The matrix and transposition actions and with the necessity of that.
Okay.
When will be the
So I think I'm not going to try to go there. So if you have the interaction system, so you have for your chips. So if you have of data, so you're going to put first bit here, the other bit one, the other bit here, the other bit here, and the other bit here, and and particular. You access all of those particulars, and then you create this form with ordered instance in the control. So this is how you open your thing. The problem is if you want to computation for you have one of it. The other is a script called pitch. So you can do the computation. So that the code is actually reading the data from this point of memory, putting them together, and then when they rise to the chip, they rise all of the bits here. 0.1 and this tricky. And this for the last includes all the data. So it's basically this form
A memory dependent, right?
Yeah. So it is okay. There are ways they are proprietary. The memory address. The next one with the memory is the memory control. Intel. And they have ways with fragmentation and the random. And then you just get it like I don't know where I become computation. That's the
Kelvin also probably like the little Indian and the end in
yes.
I have a question. The DPUs in FNAM are located on the memory control or each drive chip?
Each drive chip. So,
and the next question would be, I've seen, even though I'm not Linda speaking, I've seen two different types of processing methods. I see the ones where you have a memory, you have a GPU, and you fetch information from memory. I've seen others where the memory itself in each memory line, I guess, at the end, you have the little A and the U.
Yes.
And they do the computation directly in the memory cell.
Yes.
So which one do you see winning out in the end in terms of, or where do you see the industry progressing? The GPU units or in direct within memory cells?
I don't. It's bio. And there is, I don't think the second way on the Bitwise. The problem is the DRAM cells and the array itself is really dense. And the simplifier is really big. So if you try to put logic after the simplifier, you're making the arrays larger and larger. And then you're reducing the density. And the benefit of this type of system is that you have the density. So you lose the density, you're getting away with like you lose one of the key properties. And usually when people do this analysis of the computation there, they don't do it well. They don't have to model to decide around. So we don't know the trade-off. So still say the trade-off is, I don't know, 5%, but it might be actually 50 times the size of the array. And when we talk to the memory manufacturers, they actually like, don't touch the array. Like, that area is extremely complicated and it's actually optimized for storage. And if you try to add to storage, it requires a different metal, which so it adds a lot of cost to the hardware itself. So that is pretty true to the one. That is pretty true, and it does not pay off because you cannot afford there because the cost is too large. So it's to be so actually which is not that programmable and you will not be able to use it for many different applications. So there is a performance that provides a high performance, but for one single small tech, that's all. And this core programs, I am to record this because they between chip and the bank to quite like an aggregate is correct great, but like if you go in the IO circuitry of the bank, which is okay area is not there, you know, that area has more availability around for you to explore, and you can do more fancy. You don't need, you can put some fancy, but you can sim the engine, for example, without much of a problem, and which is more programmable, right? So I believe that there is a bureau that they didn't probably is going to see that in the next generation. Any further question? So thanks everyone for listening. Sorry again for my voice, but I hope I did.
Just a reminder that if you want to be part of the session, it will be in this room. Yeah, it is 033. So that's a minute. Yeah. 1 minute. I'll just check.
It's supposed to be happening.
Oh, so